Okay, A-level physics, gravity, part 2. What did we not cover last time? Couple of things. Gravitational potential energy and gravitational potential, they go together. Let's start with gravitational potential energy. When you were a bit younger, you would have understood that gravitational potential energy equals mass times gravity times height. Yeah, okay, that works on Earth when you're in a constant gravitational field, but when you consider the whole universe, it falls apart. It's inadequate. It's really a bit too junior for where we're up to now. Think about it like this. The gravitational potential energy that an object has is always negative. It's like falling into a hole, because if you moved two masses apart and you kept them moving until they were infinite distance apart, which is actually impossible, but never mind. They're an infinite distance apart, the gravitational potential energy at that point is actually zero. And if they're left to their own devices, they will gradually attract each other and move closer and closer together. The closer they get together, the less energy they have, because it takes energy to move them apart. So it's always negative. It's always a negative thing. Now we know that work done equals force times distance, and we'll call distance r. Now crudely speaking, we can just say, well, force equals big G, big M, little m over r squared. You're now really familiar with that. So if you think to yourself, well, work done is force times distance, then we just get work done equals big G, big M, little m over r, because multiplying by r means one of the r's on the bottom cancels out. Now that's a really crude way to explain it, and because the gravitational field isn't constant as you go away from an object, you actually need to use some complicated calculus to get from there to there. But for today that will do. That is our formula for calculating the work done and moving an object to a certain point. You can have a little delta here, because often the work done is the amount of work required to move an object from one orbit to another orbit, or from one position to another position. So it's a change in distance. Now the other thing that we need in this equation is a negative sign, because wherever you are in the universe, the energy that you possess is negative. The gravitational potential energy that you have is negative. Unless you get an infinite distance away from every other object, then it's zero. A bit weird, but that's just how it is. Now, let's move on to gravitational potential. Gravitational potential at a point is the work done. It's the work done per unit mass in bringing the mass from an infinite distance away to a certain point. So in a sense, it's equal to the work done per unit mass. So it's simply gravitational potential is work done per unit mass, which means it is negative big G, big M divided by r. Because instead of work done on a mass, it's work done per unit mass. So you're dividing by the mass. So it's in a sense very similar to, it's similar to G. Okay, you need to have some understanding of both the gravitational potential energy, which is equivalent to work done, and gravitational potential. So it's in the book. It makes sense if you look at it for a while and think hard about it. Okay.